Hi future GISPs. I'm going to teach you everything I learned to easily pass the GISP exam so that you don't have to study the 210 websites, 1,155 book pages, 1,700 Quizlet flashcards, and 291 videos and podcasts included in the GISCI study materials like I did when I passed. In this video, I'm going to teach you everything I learned about data transfer protocols when I studied for the exam. Knowledge of data transfer protocols is the first section under the Application Development category of the GISCI Geospatial Core Technical Exam list of knowledge categories. Before we start listing protocols, let's get clear on what they actually are. Data transfer protocols are standardized rules that define how computers and systems communicate with each other. They determine how data is packaged, sent, received, and interpreted, so that information moves accurately and efficiently between devices. In GIS, these protocols make it possible for servers, databases, and mapping applications to share spatial data without loss or corruption. Think of them as the language of data exchange that keeps every GIS system speaking the same dialect. Now that we know what protocols are, let's look at the methods used to transfer data in GIS. First, let's take a look at data exchange methods. Data exchange methods include file-based transfer, application programming interfaces, and web services. File-based transfer moves data by exporting it into formats, such as shapefiles, CSVs, or GeoJSONs. Files are often zipped to reduce size and transfer time. It's simple and ideal for static datasets shared between organizations that don't maintain live connections. An application programming interface, or API. An application programming interface defines rules that let software applications exchange data dynamically through network requests. APIs are used for live feeds or automated updates, like pulling the latest parcel data from a web service. Web services. Web services allow software components to share data over the internet using HTTP or HTTPS. They are the backbone of modern web mapping. Examples include REST services in ArcGIS Server and OGC standards such as WMS and WFS. ArcGIS servers can support both REST and SOAP APIs depending on the configuration. And now let's take a look at networks. Now that you understand how data is shared, let's talk about how it travels. Data moves across networks. Behind every file transfer or API call, there's a network moving packets of data. Here's what's happening behind the scenes. Packet-switched networks. The internet sends data as small chunks called packets rather than one long stream. Each packet includes a header with routing info and a payload with the data itself. A packet header. A header tells receiving devices where the packet is going, what order it belongs in, and which protocol to use. Internet Protocol, or IP. Internet Protocol defines how packets are addressed and routed between networks, so computers on different systems can find each other. IPv4. IPv4 uses 32-bit addresses, allowing 4.3 billion unique addresses. IPv6. IPv6 uses 128-bit addresses, allowing 10 to the 28th unique addresses. IPv6 improves efficiency and is replacing IPv4. A network interface card, or NIC. A network interface card is the hardware that connects a computer to a network. Each NIC has a unique MAC address for identification. Now that we've seen how data moves through packets, let's zoom out and look at the models that describe how networks work. First, let's take a look at the OSI model. The OSI model, short for Opening Systems Interconnection, describes how network communication works from the physical hardware to the applications we use. The OSI model is a 7-layer framework describing how network communication works from hardware to the user interface. Layer 1 of the OSI model is the physical layer. This is the hardware level. The physical layer includes cables, signals, Wi-Fi, and Bluetooth. It moves bits of data across devices. Layer 2 of the OSI model is the data link layer. The data link layer controls device-to-device communication on local networks using MAC addresses. Switches also operate here. A MAC address. A MAC address is a unique 48-bit identifier assigned to a device's network card for local routing. Layer 3 of the OSI model is the network layer. The network layer routes packets across multiple networks using IP addresses. Routers work at this layer. Layer 4 of the OSI model is the transport layer. The transport layer ensures data arrives correctly using TCP for reliability and UDP for speed. Transmission Control Protocol, or TCP. Transmission Control Protocol is reliable but slow. TCP verifies packet order and resends any lost data. TCP is used for downloads or email. User Datagram Protocol, or UDP. User Datagram Protocol is faster but connectionless. UDP is used for live data streams, video calls, and sensor feeds. Layer 5 of the OSI model is the session layer. The session layer opens and manages connections between devices. Layer 6 of the OSI model is the presentation layer. The presentation layer encrypts, compresses, and formats data for the application layer. Layer 7 of the OSI model is the application layer. The application layer is where users interact. The application layer includes web browsers, email clients, and GIS apps like ArcGIS Online or Portal. Once you understand these layers of the OSI model, you can see how information moves from one GIS device to another. Now let's look at the model that powers the Internet in practice, the TCP/IP model. The TCP/IP model simplifies the OSI model into 4 layers that power the Internet. The TCP/IP network model is a 4-layer networking framework that underpins the Internet. Each layer adds information to the packet as data is transmitted. The TCP/IP layers are network, Internet, Transport, and Application. The TCP/IP network model represents the same networking technology as the OSI model, but organizes the technology into 4 layers instead of 7 layers. The TCP/IP model begins with the link layer. The link layer is also called the network layer. The link layer handles local communication and MAC addressing. The link layer combines OSI's physical and data link layers. Next is the Internet layer. The Internet layer handles IP addressing and routing. The Internet layer is equivalent to the OSI network layer. The next layer in the TCP/IP model is the transport layer. The transport layer manages TCP and UDP connections between devices. The transport layer corresponds to OSI's transport layer. The final layer in the TCP/IP model is the application layer. The application layer handles sessions, data translation, and user-level protocols like HTTP, HTTPS, and FTP. The application layer condenses 3 OSI layers: the application, presentation, and session layers into 1 layer. Those 2 models, the OSI model and the TCP/IP model, are the backbone of digital communication. Next, let's take a look at how these networks actually transfer and share files. File Transfer Protocol, or FTP. File Transfer Protocol is one of the earliest methods for moving files between computers. It often requires login credentials and was used on ARPANET. HTTP was later created as an improvement. Trivial File Transfer Protocol, or TFTP. Trivial File Transfer Protocol is a lightweight, faster version of FTP that uses UDP. It has no encryption or authentication. Secure Shell, or SSH. Secure Shell establishes an encrypted connection over unsecured networks for remote access and server management. Secure File Transfer Protocol, or SFTP. Secure File Transfer Protocol is an extension of Secure Shell that adds encryption to file transfers. Secure File Transfer Protocol is a safer choice for sensitive GIS data. A network file system, or NFS. A network file system lets a computer access files on another machine as if they were local. Network file systems are common in enterprise environments. A server message block, or SMB. A server message block shares files and printers on local networks. Server message blocks are often used in Windows systems. A Common Internet File System, or CIFS. A Common Internet File System is a version of server message block optimized for use over the Internet for collaboration across locations. File sharing is great, but only if it's secure. Let's take a look at the protocols that keep our GIS data safe online. Transport Layer Security, or TLS. Transport Layer Security encrypts communication and uses public-private key handshakes to verify secure communications. Transport Layer Security is what makes HTTPS safe. Secure Sockets Layer, or SSL. Secure Sockets Layer is an older encryption protocol, replaced by TLS, though the term SSL, TLS is still used. A public key. A public key is used to encrypt data that only the matching private key can decrypt. A private key. A private key is kept secret and used to decrypt or digitally sign data. Encryption. Encryption converts readable data into ciphertext to protect information. Hashing. Hashing uses a mathematical algorithm to create a unique value for data. Hashing is used to store passwords and verify data integrity. A firewall. A firewall filters traffic by rules, allowing or blocking packets for security. A port. A port is a virtual endpoint that directs data to specific applications. For example, HTTP uses port 80, and HTTPS uses port 443. An access point. An access point allows wireless devices to connect to a wired network. Wi-Fi protected access, or WPA. WPA encrypts wireless traffic, replacing the older WEP standard. WPA2. WPA2 adds stronger encryption. WPA2 Personal uses a shared password, while WPA2 Enterprise uses individual credentials and multi-factor authentication. WPA3. WPA3 is the latest standard with even stronger encryption and protection against password attacks. Now that we've secured our data, let's take a look at how networks themselves are structured and managed. A network. A network is a group of connected devices that share data and resources. A router. A router connects multiple networks and directs packets based on IP addresses. A switch. A switch connects devices within a network and routes frames using MAC addresses. Network segmentation. Network segmentation divides large networks into smaller parts to enhance security and speed. A local area network, or LAN. A local area network covers a small area, like an office, and offers high bandwidth. A campus area network, or CAN. A campus area network connects multiple LANs across an organization or campus. A metropolitan area network, or MAN. A metropolitan area network covers a city-sized region. Metropolitan area networks are often used by municipal governments and universities. A wide area network, or WAN. Wide area networks connect networks across large distances. The Internet is the largest example, though wide area networks typically have lower bandwidth than local area networks, campus area networks, or metropolitan area networks. Bandwidth. Bandwidth is the amount of data that can be transmitted per second. More bandwidth means faster transfers. Latency. Latency is the delay between sending and receiving data. Lower latency means faster response. Throughput. Throughput is the actual rate of successful data transfer, reflecting real-world performance. Now that we've covered how networks are organized, let's look at the protocols that power the web applications we use every day. Hypertext Transfer Protocol, or HTTP. Hypertext Transfer Protocol transfers information between web browsers and servers. Hypertext Transfer Protocol powers most web applications. Hypertext Transfer Protocol Secure, or HTTPS. Hypertext Transfer Protocol Secure is the secure version of HTTP that uses TLS or SSL to encrypt traffic and protect sensitive information. The Domain Name System, or DNS. The Domain Name System converts human-readable domain names like the GISCI.org into numerical IP addresses computers can use. Representational State Transfer, or REST. Representational State Transfer is a lightweight architecture that uses HTTP and supports JSON and XML. Representational State Transfer is used in GIS web apps and APIs. Simple Object Access Protocol, or SOAP. Simple Object Access Protocol is an XML-based framework that follows stricter rules and offers more security. Simple Object Access Protocol is often used in private enterprise systems. REST versus SOAP. REST is efficient and popular for public web services, while SOAP is better for secure enterprise environments. ArcGIS servers can use either depending on configuration. In GIS, data transfer protocols make it possible for desktop software, servers, and web applications to work together. They allow data to move securely between databases, APIs, and map services. whether you're publishing a feature layer, consuming a web map service, or streaming real-time sensor data. Understanding these protocols gives you the foundation to design, manage, and troubleshoot distributed GIS systems with confidence. Now you know everything that I learned about data transfer protocols to easily pass the GISP exam. Don't forget to thumbs up and subscribe so I can keep helping people pass the GISP exam and achieve the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is a comprehensive, graphical, all-in-one resource that makes studying easy. Thanks for joining me, and congratulations in advance on passing the GISP exam.